All righty. So we're going to look at a really cool application today of using a derivative. And it basically, the problem itself presented itself generations ago, particularly before technology was around. So how does somebody calculate a square root or different things? You know, when there's no technology, we have different ways of doing it that are really, really good. But here's the question I have for you today. All right. Let's say I don't have a calculator, all right? And I want to do something like this. I want to, let's say, I want to estimate, 4.02 to the fifth power. And let's just say I don't have a calculator. Okay, you say, well, why wouldn't you have a calculator? Well, calculus was around for 400 years before calculators were around, and everybody could do everything just fine. But if I wanted to calculate that, I really don't want to do pencil and paper and longhand. I want to get a reasonable estimation. So you could start by saying, well, if I just said 4 to the fifth power, would that be reasonable? It wouldn't be too far off, but that little growth there is going to change things a little bit. So let's consider, all right, let's consider f of x is x to the fifth power. So if I said, what does the graph of that look like? In the first quadrant, certainly it's going to grow really fast. And let's say right here is the point 4 comma f of 4. All right, so it'd be 4 comma 1024. There's 4. I want the y value at 4.02. Well, that might be a little bit hard to find, but let's just say it's roughly about there. Okay. I want the y value that's just a little bit further away. Now, how can I use calculus to help me? Well, what does a derivative tell me about any function? It tells me the slope of the tangent line at any point on that function. So what if we drew the tangent line at the point that I know, and then I said, let's find the y value on the tangent line. If I use the y value on the tangent line, that ought to be very close to the y value on the curve. Now, the tangent line is passing through this point. The tangent line isn't also passing through 4.02. That would be impossible. That my line would have to bend. But the tangent line and the curve ought to be very close together because I'm not moving very far. So if I blew up that picture hugely, it'd be kind of like this. Here's the curve. Here's the tangent line. Okay, I know it's not a very accurate picture, but that's kind of what it would look like. Let me draw a little thing here. So if I made a little right triangle here, this x value, that point right there is 4 comma f of 4. That point right there would be 4.02 comma f of 4.02, whatever that is. And this point here, that would be 4.02, sorry, whatever the y value on the tangent line is. But I got some news. If I choose this point right here to have my tangent line pass through, and then we'll just use the point slope formula, calculating this y value will be trivial. I won't need a calculator. This would just be simple arithmetic. So I can use this y value as an estimation of this y value because they shouldn't separate very far. It ought to be, in other words, a reasonable estimator. So how does that work? Well, we're going to introduce some notation today. On my curve, this is the actual change in x. Let me erase this. On my curve, and this is the actual change in y. Okay, so what I want to do, and the term I like to use is the happy point. You see, 4.02 presents quite a challenge if I want to calculate, but 4 is easy because that's an integer. So 4 is my starting point. I call it my happy point. You always choose a happy point, or in this case, call it happy value. All right, choose a happy value. So we're going to choose, and we'll call it x0, because that x0 always means starting point. And then what I'm going to do is shift a little bit. And then that would mean that the delta x is 0.02. That's my little bit of change in x. Okay, so what we're going to do is, and this I can say with certainty, I'll write it down here. F of 4 plus 0.02, that's the same as saying f of x0 plus delta x, by the way, is equal to f of 4 plus delta y, right? So this is 4 comma f of 4, and this is my new point. That distance between them we called f of y. So this is absolute. That's easy, that's hard. But what we're going to do is we're going to estimate this. That's what squiggles mean. Squiggles technically means asymptotic, but in this case it also means estimate. It can't mean equal. It would be impossible for them to be equal because I have separation. But we're going to estimate it using this value. So what we do is the notation we introduce is on the curve, the change in x is delta x, the change in y is delta y. On the tangent line, we call the change of x dx, but dx clearly is the same as delta x because the change in x on the line and the change of x on the curve is the same. Oh, but the change of y on the curve and the change of y on the tangent line are not the same. So we call this piece right here dy. Now, in this case, this is one of the rare times in calculus we call the dx and dy actually quantities. They are actually called differentials. Dx, dy, delta x, and delta y all represent physical quantities. They represent measurements, distances, basically. So what we're going to do is we're going to estimate f of 4 plus delta y with f of 4 plus dy. And I'm guaranteeing you dy will always be simple to calculate. Now, how do I calculate dy? Well, I said before the point slope formula. So let me erase this because I don't need that right now. Now, what is the point slope formula? Well, if you remember, the point slope formula is y minus the y coordinate equals slope times x minus the x coordinate. So in this case, it'd be y minus the y coordinate. Remember, we're passing through this point. So y minus the y coordinate equals the slope. Now, what would the slope be? That'd be the derivative of this function evaluated at 4, because I want the slope of the tangent line passing through this point times x minus the x coordinate. Okay, this is the equation of the tangent line. Now, nice thing is, when I go to this point right here, y minus the y coordinate, wait a minute, y minus the y coordinate, that's dy. That's exactly what dy is. X minus the x coordinate, that is dx. Remember, we're going to put a 4.02 in for this at one point, and we're going to try to figure out what's the y value when x is 4.02. So dy is simply the derivative dx. Oh, well, that's not bad. In fact, that's going to be a fairly simple thing to calculate. So here I'm going to put this is equal to f of 4 plus f prime of 4 times dx. But dx and delta x, we said, are the same thing. Okay, so the formal way of stating is, this is what I want to find, but let's say I lack the technology to find this. Okay, then I can do an estimation by using a tangent line. So this topic is often referred to as simply as tangent line estimations. The way I like to think about it is the tangent line leaves the curve, but as long as I don't go too far, the value on the tangent line and the value on the curve will be relatively close together. So the tangent line is a great estimator. Now, obviously, if that change were huge, right, the tangent line and the curve would be very far apart. I can still do this, it just wouldn't be very accurate. So let's actually do this calculation. So let me go back up to here. I don't need the picture anymore. Okay, let me erase the picture. So what I do need, I need the derivative. So if f of x is x to the 5th, then f prime of x is 5x to the 4th. Okay, f of 4, that's 4 to the 5th power, so that's 1024. F prime of 4, which would be 5 times 4 to the 4th power, that would be what, 1280. And my dx is this. So now I can actually finish the problem. we can say that f of 4.02 is equal to 1,024 plus delta y, but that's going to be estimated by 1,024 plus 1,280 times 0.02. So like I said, this is a really simple calculation. Now, you can use a calculator for that if you choose, or you can do that in your head. So that's 1,024 plus 1,280 times 0.02. So on my tangent line, the y value is 1,049.6. Okay, so the final way for me to answer this question, everything I've said is correct. The problem started with, I want to estimate this, and I'm going to use this value. So the formal way to finally write the final answer, that no ambiguity, squiggles, it is not equal and it's not an approximation. An approximation is like pi or square root, where you have an infinite decimal and you've got to round it off at some point and report that. That's an approximation. An approximation requires technology, absolutely. You're doing estimation. You're not saying they're equal, you're just saying they're ballpark, they're close. Estimated with this. So this is the final answer. Now, I'm pretty sure this is correct. I'm pretty sure I did a good job on this one. I might have got a decimal wrong somewhere. I might have made a bad calculation. Heck, I might have hit the wrong button on my calculator. Is there a way to be absolutely certain that I did this problem correctly? Yeah, you're going to do something the previous generations couldn't do. You're going to cheat. In other words, actually find out what is 4.02 to the fifth power. 4.02 raised to the fifth power is, it actually, whoops, just erased it. Raised to the fifth power is, there we go. 1,049.8572.832. 1, 2, 3, 4, 5, 6, 7. I lost a decimal somewhere. I don't know. Well, that's as far as my calculator will give me. My graphing calculator would give me more decimals. This is the actual value if I use my calculator. This is our estimation. I don't know about you, but I say that's pretty darn close. I have an answer that's over 1,000, but it differs by only about 0.25. In other words, that's a very, very good estimation. But 0.25 is a lot, not compared to 1,000, it's not. Okay, so that, in other words, that's a good estimation. And so this is the answer. So this is this problem, but I want to give you then the general. Okay, how do I do this in general? Is there an actual formula? Yes, there is. So we'll do that next. Like I said at the beginning, for those who are here, we did this problem to start my Calc 3 lecture on Tuesday, and then I did the three-dimensional version of this. See, we have a curve and a tangent line that's really close to the point that I'm looking at. In 3 dimensions, you have what's called a surface, and then you have a tangent plane. And then you move to an icky place on the surface and use the tangent plane to estimate the ugly one. See, we estimated the ugly number using the happy number. So here's how it works. Okay. We know f of x naught. That means x naught is our happy number. We know f of x naught. That's trivial. Okay. What we want to do is estimate f of x naught plus some change in x. That's what we just did in the last problem. In the last problem, we knew f of 4. We were estimating f of 4.02. Okay, that's it. The way we do that is f of x naught plus delta x is equal to f of x naught plus the actual change in y. That is always the case. Problem is, we can't find the actual change in y most of the time. That requires technology. So we estimate this with f of x naught plus dy, where dy is always equal to f prime of x naught dx. That should always be a simple thing because you're using the happy number, not the icky number. So it doesn't matter what the question is, you can always do this. So let's do another example of this. Okay. Let's walk our way through this because it's kind of a cool thing. And you can do this for complicated things. Let's say we want to I want to estimate, how about the cube root of 7.98? Actually, let me use it. Let's 7.96. Sorry, I want to use a different value this time. Let's see. Would that be a good one to do? Actually, you know what? I want numbers that come out really nice. I want to cheat a little bit. I'm going to change it slightly. Sorry, I want a bigger number. Let's say 26.96. Yeah. I want to estimate the cube root of 26.96. You know, well, they could do that forever on a calculator. You do realize a root key didn't exist on a calculator for the first 10 to 15 years that calculators existed. They only added, subtracted, multiplied, and divided for about 10 years. And if you wanted a calculator with a root key in the early days, you were going to pay for that calculator. So I want to do this. All right. So now we have to set up the problem. What is my f of x? See, I didn't give you a function. I just asked you to calculate a number. Anybody want to guess? What should we call our f of x? Just holler out. What should my function be? There aren't really a lot of choices. Anybody?
Just x to the 1/3?
X to the 1/3. The reason I have to have a function, I actually have to create a function, is I have to be able to take the derivative of something. Now, what should my happy number be? What is my x0? Well, I don't know the cube root of 26.96, but I do know the cube root of 27. So you pick your happy number to be the closest easy number you could work with. Okay, so that's a no-brainer. Now, what is my dx, which is the same as delta x? What is the dx or the delta x in this case? You gotta be careful, because remember, you're adding delta x or dx. This one always throws everybody. What is my change in x going to be?
Negative 0.4.
Negative 0.4. By the way, this right here is the single most common error people make. Is, oh, I moved 0.04. Yeah, but you went backwards. Well, how do I know it's negative? Because you're always adding it. And here's the error. If I put 0.04, then I'm not estimating this. I'd be estimating 27.04. So if you're less than the happy number, then you're going backwards. That's it. That's why I'm doing this example. The change in x can be positive or negative. That's not a big deal. But if I get that wrong, I will do this whole problem. I'll get an answer, but I'm answering a different question is essentially what it comes down to. So with this said, let's do our calculations. What is f? First of all, what's f of 27? Well, that would be cube root of 27. That'd be 3. What's f prime of x? That's 1/3 x to the negative 2/3, or 1 over 3x to the 2/3. Okay. Therefore, what's f prime of 27? Well, if I put a 27 in here, the cube root of 27 is 3. 3 squared is 9. So this would be 1 over 3 times 9. That's just simply 1 over 27. Okay, and then we've got this. So we actually have everything we need now to answer the question completely. So I'll write it in formal terms. F of 26.96 equals f of 27 plus delta y. And that's going to be estimated by 3 plus, now what's my dy? My dy is the derivative multiplied by the change. Okay. That's it. That's my estimation. Now, I will use a calculator because that's going to be a decimal value. So I've got 3. So my calculator says, and I'm going to write a lot of decimals. My calculator says this is approximately what? 2.998518519. There's going to be a repeating decimal sequence at some point. Looks like, yeah, 815 or 851. It's going to do that forever. So I'm going to write it like this. So now I can see it's exactly this. See, I'm being clever. I'm recognizing the repeating pattern. Remember, all fractions have either a terminating decimal or a repeating pattern.
Shouldn't that equal also be in the equivalent squigglies or no?
Well, this quantity is equal to this.
Oh, okay, sorry.
Okay, so now we're done. Let's answer the question. The question, where is it? I'll put it up here. So therefore, the cube root of 26.96 can be estimated by 2.99851. And by the way, if you decided not to write that, just give a terminating decimal. It's not really that big a deal. Now, does that answer seem reasonable to you? Well, without a calculator, don't we all agree the answer should be a little less than 3? I mean, we all agree that it should be a little less than 3 because that cube root of 27 is 3. So when I do the cube root of this, so let me do the cube root of this, 26.96, the actual value on my calculator, you love this. My calculator says the answer is 2.998517. It doesn't differ until the 6th decimal place. That's pretty powerful. Wow, because the next number here would be 8. On my calculator, the next number is 7. So even though this isn't equal, we got the first 5 decimals correct. I'd say that's pretty accurate. Why is that? Because the line did not separate from the curve very much. So this is a very powerful form of estimation. Now, this isn't where this is used entirely. This is used in other areas, namely in measurements. Now, I went over this in my Calc 3 because it makes a little more sense to them. If you've ever had statistics, in statistics, the most important thing we study is what's called variance. In fact, there's portions of the class ANOVA. Some of you may have heard that term. That's analysis of variance. If you take statistics long enough, you realize you don't talk, the mean is nice. It's always the variance that you're studying. Variance is sort of a numerical measure of consistency, if you think about it. So if you're, let's say you have a bottling plant and, you produce thousands and thousands of bottles go through and you get filled up, and the average is always what it's supposed to be, but every individual bottle is all over the map, right? Some are too full, some are not full enough. I have very inconsistent production. Variance is a numerical measure that measures the consistency, basically. So when variance is large, that means I have a large spread. If variance is small, it's a very tight spread. In a perfect world, variance would be 0, but it's not really possible. Think of IKEA furniture. I love using that example. And by the way, I'm not knocking IKEA. We have a lot of IKEA stuff. IKEA furniture, right? You get it and there's no words in the instructions and you're putting it together and the things fit perfectly, right? The prongs always fit in the hole. Everything always works perfectly, or does it? Every now and then you could have the holes drilled just being off enough that things don't fit. It's possible, okay? In that part of the world, those are called tolerances. Is it possible to have error? Absolutely, you can't be perfect. So there's what's called acceptable error or tolerances. So when those things are fitting into the holes and all that stuff, maybe I can be off by 1 millimeter, and that's totally okay. But maybe 5 millimeters is too much to be off. I don't know. But there would always be a maximum amount of error that would be acceptable before it's not going to fit anymore. It might be a tight fit, but it still fits. So how do you measure things like that? Well, that's what we're going to do next. So if variance is a measure of consistency, then what we're going to look at is there a way of actually calculating your maximum error? Or in other words, will you exceed certain tolerances based on the given information? Now, if you are running a business, you need to know what sort of error you might have. So for example, if whatever it is you're doing, maybe you have a bottling plant, maybe you make cars, I don't know. But if the error is too large, you're going to have too many of your items returned, and that's going to cost you a lot of money. But replacing your machines is also extremely expensive. So think of it another way. When you go to the grocery store and you buy that bag of chips, you know, it says 14.6 ounces, and then you open up the bag and you look in the bag and hello, hello. You know, you got the echo because there's this all air. You know, and it says some settling may occur, but you're looking at that bag going, I don't think I got my full bag of chips. So you go and you weigh it and turns out you're way short. Well, by law, anything sold in the United States that doesn't meet what the claim is, like in this case, it's short, it has to be replaced. The Department of Weights and Measures is the overseer. That's a big federal government bureaucracy thing that if you went to a gas station and you noticed that the pump was always shorting you, it says it's got this many, but you know it was short. You called them up, they go out, they check it out, they bust those people. The fines are like in the millions and millions of dollars. People don't want to mess with that. So if a store was shorting customers on an item and you complain, they don't have a choice. They have to replace the item. That's by law. If you went to a restaurant and you order a 16-ounce steak and you got a little 8-ounce steak, you do not have to pay for that 8-ounce steak, and they have to replace it and make it right if they actually want to get paid. It's not even an issue. So when you short people, you have to replace it. That's the law. That's never going to change. But if you give too much, then you're giving away product. Ooh. So in other words, both cases are bad. If you short people, you got to replace it. If you have too much, then you're giving it away for free. When I go to Sprouts and I see that, 10-pound bag of potatoes, is there even a chance it's exactly 10 pounds? No. Potatoes don't all come the exact same size unless they're going to have a partial potato. That bag might be 9 3/4. It might be 10 1/2. So what I do is I weigh them and I find the bag that's 10 1/2 and I buy that one because there's no way it's ever going to be exactly 10. But if whoever's doing the loading is constantly having 9, 9 1/2, 9 3/4, nobody's buying that bag. It's getting thrown out. Oh, okay, so let's give them all extra, but you're charging them for a 10-pound bag, but you're giving them 10 1/2. So again, inconsistency is expensive. So here's what we do. We make cubes, okay? Cubes are us. We make cubes of all sizes, right? Our cube could be a sugar cube. It could be one of those pods, those things that sit in your driveway and you intended to move it, and a year later it's still sitting in your driveway with all your stuff. Yeah, they grab hold of the concrete, I think. Right? But we make cubes of all sizes. And so what we're going to say is that the measurement of the cube, let's say the maximum error, darker ink, the maximum error in an edge is 1%. An edge would be that. You don't say a side. A side is ambiguous. If you use the word side, all human beings are going to think you mean a square. Nobody calls that a side. A side would be the whole. So you use words like edge and face, which is kind of weird, I know, but the edge. So the maximum error is 1%, let's say. Now that's whether it's a sugar cube or whether it's a gigantic pod, we're going to say the most it can be off is 1%. Okay, that's simple. So the question is what we want to do is estimate the maximum error in the volume. By the way, it won't be 1%. So 1% might be totally acceptable. I can be off by 1%. But what if the maximum error in the volume ended up being 10% or 20%? You'd say, no, that's I'm giving stuff here and I'm either way too much or way too little. So you got to be really careful. Now, when we say the maximum error is 1%, we don't mean everything's off by 1%. We mean that's the most something can be off. So things could be right on. Now, we're going to enter something slightly different. Okay, so let me give you a simple example today. All right, so today on the job, let's say that William was off on his job, he was off by 20 centimeters. And Nate on his job today was off by 10 centimeters in the measurement of what he was doing. So who had a better day at work? You do realize you can't answer that. William was off by 20 centimeters, Nate was off by 10. Well, doesn't it kind of depend on what they were doing? Oh, William was putting a beam on a skyscraper that was, let's say, 100 meters across, and the tip of his beam was off by 20 centimeters. He was so annoyed, his 100-meter beam, he was off by 20 centimeters. That's 20 centimeters compared to 100 meters. That's 1/500th. That's 0.2%. That's microscopic. Now, Nate, on the other hand, was performing open heart surgery and was off by about 10 centimeters, which, by the way, is about how big a human heart is. In other words, he was off by the size of the heart doing the surgery. So, of course, he killed the patient because he only had 10 centimeters and he was off by 10. That's 100% error. So you see, when you're talking about error, it's never the amount of the error. It's the percent of the error. That's called relative error. And this is something we want to get used to. So relative error in this case would be delta V. That would be the actual error over V itself. Relative error is generally always expressed as a percent. So another way of thinking about this, if you came up to me and said, oh, Mr. Brown, I got 87 on the exam. My first question is 87 out of what? Oh, out of 1,000. Ooh, that's not so good. Out of 88. Oh, that's fantastic. But if you said I got a score of 87, that doesn't tell me anything. But if you said I got 87% on the exam, oh, now it doesn't matter how much it's out of. It doesn't matter if it's out of 100 or 100 million, you got 87%. That's a relative score. So if you just said, here's how many points I got on something, that doesn't mean anything unless you points out of how many. See, the points out of how many is what the relative score would be. That's why we use a percent. A percent is unitless. Okay, so what we want to do is do this, but we can't calculate this easily. So we're going to estimate it with dV over V, and we're going to use the exact same formula we just used a moment ago. It means we got to have a derivative and that kind of thing. So where's a derivative going to come from? Well, the volume, if I call each edge x, then the volume will be simply x cubed. So volume would be a function of x. The 1%, that is not a value. That if I said, oh, my edge is off by 1%, 1% is not a measurement. 1% is a ratio of the error over what it's supposed to be. So that means that dx is at most 1% of x. That's kind of like if you put your money in the bank. And I said, oh, I'm putting my money in the bank and I'm getting 5% interest. Well, how much are you getting in interest? I'm getting 5% interest. Yeah, but how much money is that? Well, it's 5% of the amount I put in. 5% isn't a dollar amount. It's 5% of what you put in. Therefore, interest divided by what you put in is 5%. In this case here, the error, the maximum error is 1% of what it's supposed to be. So you could also say it this way, that the ratio here would be at most 0.01. And that's 0.01 too big or 0.01 too small. We don't care when it comes to error. It doesn't matter if it's too big or too small. It's just how far are you off. I'm throwing darts at the dartboard at the bullseye. And I said, oh, I missed the bullseye by 2 inches. And then somebody says, yeah, but was it 2 inches too high or 2 inches too low? Was it 2 inches to the left or 2 inches to the right? No, I missed it by 2 inches. Does it really matter what direction? I was 2 inches off. So I threw 4 darts at the dartboard. One was exactly 2 inches above, one was exactly 2 inches below, one was exactly 2 inches to the side, and one was exactly 2 inches to the side. So does that mean on the average I hit the bullseye? No, that means on the average you were 2 inches off. That's how it works. You don't get to say all my errors put me exactly where I'm supposed to be. No, not quite. So we want to do this. So all I have to do is take one derivative here. And the derivative I'm going to take is right here. So dv dx, or if you want v prime of x, is simply 3x squared. Okay, that's my derivative. That's v prime of x, if you will. So here's what we know. We know that delta v can be estimated by dv, and dv is the derivative times the change. And this is exactly what we just did with the numbers, the derivative times the change. So delta v over v can be estimated by dv over v, which equals 3x squared dx. Dx is a physical value in this case, over x cubed. And you notice I get some really nice cancellation here. That's going to be 3 times dx over x. But we said dx over x is at most 1%. So if the error in the measurements of each edge can be at most 1%, then the maximum error in the volume we estimate at 3%. So the final way of saying this is delta V over V can be estimated by, and I would just say 3%. Now, here's why this is so important in real life. Well, 1% doesn't seem like much of an error, but depending on what you're doing, maybe 3% is too big. You see, when you're selling cubes, you're not selling edges, you're selling the whole cube. And if an edge can be off by as much as 1%, maybe you can live with that, but the volume is off by as much as 3%. That might be too much. You know, if I'm filling cans at the grocery store, you know, whatever the product is, shorting a customer 3%, that might be too much. Giving them 3% too much might be giving away too much. You might say, no, I want the maximum error in the volume measurement to be smaller. I want that number smaller. So that's where you would have to replace the machines and things like that, as we talked about. So in real life, this is how companies make decisions. They use the fact that, okay, if I can be off by this much, what is the bottom line then? The product I'm creating, how far can that be off? And you might find that it's too much. So then we have to change the way we do things, because, you know, if money's at stake, calculus becomes your critical tool. All right, so we're going to move on from this. This is a cool application. Now we're going to do something a bit more theoretical. I'm going to introduce a new concept here. So I'm going to do a quick review of complex numbers, because we're going to be doing the one time calculus uses complex numbers, the only time in calculus you use complex numbers. After you finish the calculus series, right, 150, 151, 252, every math class after that, pretty much you're going to use complex numbers. But we do the calculus of real numbers, so real input, real outputs, with one exception, because it's a very important type of function. So to remind you, okay, what is the square root of -1? Anybody remember what that is? What symbol do we use for that?
I.
We use I. Now, I put a tail on my I, because if I don't, it ends up looking too much like a 1. So now, can you calculate the square root of -1? No, this is a definition. So this is one of those 3-bar things. In case you forgot, you've used this before. I'll show you. We used this on the first day of class, if you remember. On the unit circle, the cosine of theta is defined to be x. It cannot be calculated. That's the definition of and the sine of was y, and the tangent was y over x. You guys remember this? Oh, but if I do this, then tangent will equal sine over cosine. That's a result. That's not the definition of tangent. No. The definition of tangent is this. This is a result of the definition. So I use an equals because I can actually show that. The 3-bar means is defined as. The beautiful thing about that is you don't have to prove it. It's like when you look up a definition in the dictionary, nobody has to prove it. That's what it means, that you use that. So with that definition, we build an entire system of numbers, which is actually the main way we do things later. Later on, you'll see everything's complex, but for now, not so much. So if that's the case, then technically I is a square root. So if I asked you, what's the square root of -9? Well, if I is if I just have a square root, I still have rules of square roots. And you remember the root of the product is the product of the roots. So I know from baby algebra, I could do this. But this is 3 times I. This is a result. That's not a definition. That's the definition. This is a result of the definition. So that means also that I squared is -1. Groovy. What would I to the fourth power be? Anybody want to try one? What's I to the fourth?
-1.
-1. If I square this,
1.
yeah,
1.
I can get real numbers back. In fact, when you square I, you do get back a real number. So that we know. So we generally use the following when we say complex number. We say anything of the form, and I'll use the letter Z, Z equals A plus BI, where the A and the B symbolically, that means the real numbers. We usually use a script R. So this says A and B are elements of the real numbers. In simple English, if you take any two real numbers and then you write A plus B times I, B is a coefficient, therefore, of the I, this is what we define as a complex number. Okay, so a lot of us aren't really familiar with this. We didn't do a lot in pre-calculus. Maybe you did a bit with the Mont's theorem. That's where you're finding all the roots of weird things and stuff. But if that's the case, then we say any number that can be written in this form, any number that can be written in that form is called a complex number. And we say that Z is an element, and then we use a script C. Okay, that's again universal notations. We use a script R for reals, a script C for the complex. Then if I said, is 6 complex, just the number 6, I said any number that can be written in this form, is 6 a complex number? I know it's a real number.
If we had say I to the fourth power, where it would be 1, no?
No.
Oh, then no.
Can
Oh,
I
it just
write
has to be-
6 in this form?
Can you just write 6 plus 0i?
Oh, that's 100 miles. You get 100 miles for that one. Is this a correct mathematical statement? Yes. Did I write it in this form? Yes, I said A and B are real numbers. I didn't say that'd be positive numbers. I just said that'd be real. That means that every real number is a complex number with 0 imaginary part. Oh, how about, okay, is 5i complex? Well, that should be easy now. Is 5i complex? Every real number, turn off, probably Nate, okay, please mute yourself. That's louder than me. Every real number is complex with 0 imaginary part. Every imaginary number is complex with 0 real part. So usually the implication is when we talk about complex numbers in general, we're saying numbers of this form where these guys are not zeros. I mean, technically they could be, but we're not talking about, if I'm talking about real numbers, I'll say real numbers. If I'm talking imaginary, I'll say imaginary. But if I'm talking about the mix, we use the term complex numbers because they have their own set of rules and rights and privileges and all those kind of things. So I just want you to remember what they are. Now, the algebra of complex numbers, that's a whole nother thing. Hopefully in your pre-calc, you did things like that. You figured that out. But I want to show you something. This is something you may or may not have been exposed to. There's a lot of math you've never seen that's there. And a lot of times you don't learn it till later. Okay. That generally means imaginary. This is what's called the complex plane. This actually is the way of the world. You just don't see it right now. You'll see it later in math. The complex number plane. Every value, or excuse me, every point on the complex plane represents a complex number. In other words, this ordered pair, we say it's equal to A plus BI. This is the way we deem the complex number plane. Every ordered pair on the complex number plane represents a complex number where the first coordinate's the real and the second coordinate's the imaginary component. A and B are real. A plus BI is the complex. Therefore, in math, we talk about the real number line. Everybody remembers that from baby algebra, the real number line. Well, the horizontal axis on the complex number plane is the real number line. Everything on this has a y coordinate or a second coordinate of 0. Oh, okay, so every real number can be represented as a point on that line. Every purely imaginary number can be represented as a point on that line. Therefore, when something has both parts, then it's a point in one of the quadrants. Now, this is absolute. This is how most all the math that you go later on comes from this. So, I want this distance right here. Okay, let's call this Z. Okay, let's just call that Z. I want distance. Now, when asked for distance, first of all, we all agree distance has to be non-negative. And distance could be 0. If I said, how far am I from where I'm standing? What? I'm 0 from where I'm standing because, oh, how far am I from the other side of the room? Well, do I say this minus that, or do I say that minus this, or are both correct? So whenever we think of distance, that's where absolute value comes into play. Okay, because absolute value can't be negative. So when we're talking about how far away two things are, the order of subtraction is irrelevant because you're technically doing the absolute value in a sense. And the distance formula, okay, was the sum of the squares. I got that. So if I said, how far is this? I think we all agree that this would be the square root of a squared plus b squared. I think we all agree that that distance. Okay, a and b are real numbers. I think we can agree on that. I'm leaving out sines and cosines for the moment. They'll come back in later, but we all agree on that. Well, it turns out if I wrote this, then that would be a true statement. Now, that back in pre-calculus, when you took a complex number and you put the vertical bars on it, the term they used was, let's see if you remember this, modulus. Does anybody remember this? Yell at. Does anybody remember that term from pre-calc? Maybe in trig, if you were lucky, you did some complex. They'd say the modulus of a complex number. And then they would say things like, well, we use the same type of notation as absolute value, but it's not absolute value. It's nothing to do with absolute value. That was a lie from the pit of hell. This is actually the definition of absolute value. That is absolute value. Modulus is a made-up word. Modulus is absolute value. I don't even know why we bother. So you will never hear that term again in a math class, probably the rest of your life, because it's absolute value. What is absolute value? Absolute value, if you're explaining to your younger sibling who's in elementary school and they first talked about absolute value, you said to them, I have a number line. And if I said, what's the absolute value of 5? Well, it's the same as the absolute value of -5. Because absolute value is how far away is a number from 0 on the number line. That's what you were told when you were kids. And by the way, that's a good definition. There's nothing wrong with that definition. Oh, that's why -5 and +5 are both 5 units from 0. So their absolute value is 5 in both cases. Okay, great. But on the complex number plane, that means I'm only talking about numbers on the real axis. Oh, what if I have a number here or a number here? The distance, this is still 0. See, the origin on the complex plane still represents the number 0 because it's 0 plus 0i. So complex numbers have a distance to 0 that's it's measured using the Pythagorean theorem. So this actually is the definition of absolute value. Absolute value is the sum of the squares of the components, right? And that's it. But because we generally are only been dealing with real numbers, there was never a second part. Oh, so most of you know this one. If I said, what's the square root of x squared? We should know that's absolute value of x. And most people say that's the definition of absolute value of x. Well, it's the definition if x is purely real, yes. But if x were complex, that would not be true. See, if x were complex, I'm missing a piece. If x were imaginary, that's not exactly true. So you got to be a little bit careful. This is only true if x is real. Oh, there's got to be a second term if it's complex. So that's the definition of absolute value. That's an important thing. I know some of your brains are going, oh my God. No, we're not going to reinvent mathematics. We don't do that till later. By the time you get to diffie-q, then we'll reinvent. But by then you'll be ready for it. So now I'm going to throw in big piece of the puzzle next. Okay. And a lot of you saw this in pre-calc, but you may not remember the details. Now, still complex, but now I want to have 1. This is called the unit complex circle. Okay, we are on the complex plane. We know what a unit circle is in the XY, regular XY plane. This is called the unit complex circle. Okay, now that's theta. I know this is still cos theta sine theta. That doesn't change. That's still true. I mean, sine and cosine, theta is real. That's not weird, but this represents cos theta plus sine theta times I. Oh, remember a plus bi? That's what this represents. Huh. Now, hopefully you guys have seen something like this before, typically in both trig and pre-calc. Now, I want to show you something about a notation thing that people generally do. When you see this, you generally see the I written in front. That doesn't make it more correct. It has nothing to do with correctness. It makes it less likely to be misinterpreted. If I wrote, let's just say something like this. If I wrote the cosine xy, is this the cosine of x times y? Or is this the cosine of the quantity xy? Or is the correct answer, I can't tell? Anybody want to guess? You have three choices, this, or can't tell.
Can't tell.
Good, that's the correct answer. This is the worst possible notation anyone can use. And by the way, I find most calculus books will do this for both. That's bad. No. If my argument is the product of x and y, I absolutely have to have parentheses. If my argument is just x, then technically order of operations say I'm going to do the cosine first. But if I wanted this, then what I should have done is put the y in front. Why in the world, and by the way, some of us are guilty of this, why would you put the y after when it might be misinterpreted? Oh, so that's why in all of the math books, you always see it written this way, because otherwise there's the problem of saying I have a product, unless I put some space between these, you see the obvious potential error there. And then others will say, wait a minute, obviously I'm multiplying the quantity times I, you can't have an imaginary angle, right? Actually, you can. In fact, you've been using imaginary angles for a really long time. You didn't know it. I'll give you a hint, at least half the time you're using imaginary angles, at least half the time. And I'm going to show you in a minute, and you didn't even know it. No, it makes theta times I makes perfect sense. That actually is legit. So that's why the books often write it this way. Okay, now that's my z. And again, if I said, well, how far is that? Well, it'd be cos squared plus sine squared, which is 1, a squared plus b squared under the square root. Cool. Now, this gives rise to probably the single most important identity in all of mathematics. E to the I theta equals cos theta plus I sine theta. In other words, every point on this circle, for every possible value of theta, clearly I will sweep out every point on the circle. But this is equal to this, e to the I theta. Yes, this is considered one of the single most important, well, it's a non-calculus formula, but it is an identity that, believe it or not, relates real and imaginary circles, triangles, the hyperbolic functions, the logarithms, exponential functions. Most of mathematics, there's a glue that holds it together, and this is the formula in many cases. This formula is so important. This formula is so important that, believe it or not, there are American sports franchises, or I should say North American sports franchises, that were named after the guy. Yeah, the guy that came up with this formula several hundred years ago. We have franchises, which people find absolutely amazing. Okay. You said sports franchises? Yeah, Wayne Gretzky started with this team his first 10 years of his career, the greatest hockey player of all time. If you don't know anything, they're up in Edmonton. Yeah, Tennessee Titans actually came from Houston, and then they moved to Tennessee. Anybody know what the guy's name is, of course? It's
the Oilers, right?
The Oilers, yep. The Edmonton Oilers in hockey, the Houston Oilers in football. Their owners were big math guys. They were huge math fans. And
This is like the movies again, huh?
Well, at least, okay, that's my interpretation. Okay, I'm going with that. Yeah, 2 sports franchises were named after this guy. That's how important the formulas are. Yeah, this is Euler, not Euler, Euler. Euler's formula, and hopefully all of you have seen that and worked with it in both trig and pre-calc. So why am I saying hopefully? Because that's actually considered one of the top 3 things in both of those classes, according to the state of California. So if your teacher didn't spend like 2 weeks on that at least, then you got shortchanged. You can ask for your money back at this point. I don't need you to know this, but it does help if you're a little bit familiar. Now, Euler's formula is how we get to the next thing we're going to do. This is an identity. This doesn't have to be proved. So he said, what do you mean? Imaginary angles and so on. Well, here's one of the beautiful things. If I replace theta with an imaginary angle, okay, replace theta with an imaginary thing, then I times that imaginary thing will be real. If I use an imaginary angle, I get a real output every time. Oh my gosh. Yeah. Yeah. If I replace theta with, let's just say, I don't know, pi over 2i, well, then this would be e to a real number, even though I have complex stuff over on the other side. It's crazy. So with that, we are now going to define what are called the hyperbolic functions. We can now define these things. Okay, it starts with the hyperbolic cosine of x. I'll write it like that, and we write it. Now, a lot of you have seen that before, the COSH, cosh. It's hyperbolic cosine. That's what it means. You all have a key, even on a cheap calculator. You all have a key. See the HYP? Hopefully you can all see that. The HYP key, and it's right there. Everybody can see that, can't they? The HYP, even the cheap calculators have them. That's how you do hyperbolic. So if I had HYP, then cosine, it's, in fact, I'll do that. HYP cosine, see what my screen says? Even the cheap calculators, you can do a hyperbolic cosine. That's not a big deal. The hyperbolic cosine of x is written like this. Okay, the hyperbolic cosine of x is equal to the cosine of ix. Now here's the crazy thing. If I put any real number in for x, let's leave x. X is going to be a real input right now. The hyperbolics, we're using real input. If I put a real number in here, that means I have an imaginary angle. But the hyperbolic cosine only returns real numbers. Whoa. If you take the cosine of an imaginary number, you will always get back a real number. That's crazy. But what's way cooler than that is you'll get back a number outside the range of -1 to 1. See, all our lives we've been told that the cosine function, all real numbers can be input, and that is true. And then when you do the cosine, you get a cosine wave, and therefore your output must be a number between -1 and 1. That's also true if you limit your input to real numbers. If you allow for imaginary input, then the cosine function will return all real numbers. That's crazy. I'm going to show you that one in a couple minutes too. Yikes. With that, the hyperbolic sine is -I sine ix, and the hyperbolic tangent is -I tangent ix. These are definitions, by the way, not results. So I'm going to put the 3 bars. Now I'm going to, and then I'll do one more. The hyperbolic secant is defined to be the secant of ix. These guys get negative i's in front, these guys. So these guys are usually going to return imaginary numbers. Well, no, it turns out that the sine of ix is going to be imaginary. And then when I do this, it's going to be real. So all of these return real numbers. It's crazy, but that's what it is. So these are the definitions. But that's not exactly what you're going to do when you do it in calculations every time. So let me do an example of this. Let's calculate, if you will. How about the hyperbolic cosine of number 4? So that means I got to make sure my calculator is in radian mode. Because remember, your input is always radians, not degrees. I want the hyperbolic cosine of 4. That's equivalent to asking you the cosine of 4i. I want you to calculate the cosine of 4i. No, I don't need you to do it. Use your calculator. So hyperbolic cosine 4 equals. You know something interesting about that number? Well, not only is it a real number, 27.3. I thought cosines were supposed to be between -1 and 1. Yeah, cosines are real numbers. But we're so beyond real numbers today. Oh my goodness. This is approximately 27.3. If I insert any real number, I'm going to get back something. By the way, what about the hyperbolic cosine of 0? Hyperbolic cosine 0. Well, I know the regular cosine of 0 is 1. What's the hyperbolic cosine of 0? It's 1, because I'm asking you to do the cosine of 0i, which is 0. Oh, okay, so I see some consistency there. Now, I want to go over the derivatives next. Well, I'm going to come back to the Euler's formula. We haven't used it yet. So with those definitions, I first want to differentiate the hyperbolic cosine of x. Well, that means I'm going to differentiate the cosine of ix. Now, I is the square root of -1, but I technically is a constant. It's a number. It's an imaginary number, but it is still a number. So this is the cosine of constant x. So the derivative should be negative sine of ix times the derivative of ix. Well, what's the derivative of ix? I, because I is a constant. So right off the bat, we see that the derivative of the hyperbolic cosine of x is the hyperbolic sine, not negative, it's just straight up the hyperbolic sine. Cool. Okay. Let's do the same thing with the hyperbolic sine. Oops, sorry, lost my negative I in front. I want to do that. Okay, well, this would be negative I times the cosine of ix, and then the derivative of ix, which would be I. Negative I times I. Anybody want to try that one? What's negative I times I?
Negative I squared.
But I squared is, what's I squared?
-1.
So therefore,
1.
1.
I squared.
It's the negative, like William said, of I squared. So it's the negative of -1. Oh, the negative of I squared is +1. So therefore, this is cos ix, or, oh, that's kind of convenient. The derivative of the hyperbolic cosine is the hyperbolic sine, and the derivative of the hyperbolic sine is the hyperbolic cosine. Cool. I mean, if I know those, then I can go chain rule right off the bat. I don't even have to work. So let's do an example of that. Just so we understand, I'm going to go right off the bat here. The derivative of the hyperbolic cosine of u of x is then just the hyperbolic sine of u of x du dx. That's it. That doesn't even matter if I have complex stuff. That's what it is. And the derivative of the hyperbolic sine of u of x is the hyperbolic cosine of u of x times the chain rule. Oh, how nice. I mean, that means I can do a derivative of a hyperbolic function of anything and then just write the answer. I don't have to, the fact that there's complex going on actually doesn't mean anything in terms of taking the derivatives. That's easy. I needed to show you now. I kept saying Euler's formula, where does that come in? You see, I have a cheap calculator. How did my calculator calculate the cosine of 4i? That's what hyperbolic cosine is. How does a calculator calculate an imaginary input? Well, it doesn't. It doesn't calculate the imaginary input. There's something that I can change it to. I can use an identity, Euler formula. I can use an identity to change the hyperbolics. Okay. Going back to Euler's formula. I'll actually, it's up on top. Okay, if e to the I theta is that, then let's start by having theta equal, how about, let's do theta equals negative ix. Remember, theta, there's no rules on theta. Theta can be real, imaginary, theta can be anything. Now, I want to remind you of something that what you may or may not remember about even and odd functions. We haven't really needed it so far in this class, But if you remember something, an even function, if I need this for a moment, if f of x is even, it's an even function. So an even function would be like, for example, a polynomial where everything's of even degree. That's a simple example. If f of x is even, then f of negative x equals f of x. Graphically, what that means is you have y-axis symmetry. The y-axis acts as a mirror. I try to make that look like a mirror. If you have an even function, then this point here, which is x, f of x, on the other side, I have negative x, and it's the same f of x, the same y value. So if I input a 10, whatever y value I got the same as if I put in a negative 10. What functions are even functions? Well, certainly if any polynomial to an even degree, cosine, secant, those are the most common ones. Those are even functions. So let me do a really simple example because I need that result in a moment. So if we said, for example, f of x is, 4x to the 6 minus 3x squared plus 8. That's even degree, and a constant technically is considered even degree because it's times x to the 0 power. What is f of negative x? Well, that'd be 4 times negative x to the 6th minus 3 times negative x squared plus 8, which is 4x to the 6th minus 3x squared plus 8. And that's my original f of x. Because all of these are even degree, all of them are even functions, then the sum is an even function. That's easy. That's easy to remember. We like even because sometimes they give us a shortcut. An odd function is totally different. An odd function is one that has what we say symmetry about the origin. In other words, it has what's called rotational symmetry. If I rotate the graph 180 degrees, it will look exactly the same. Now, what sort of functions have this? Well, basically any polynomial that has an odd degree, y equal x cubed, x to the 5th. Sine, tangent, think about the tangent curve, think about the sine wave. Cosecant and secant, it turns out. So an odd function is when f of negative x is the negative of f of x. So if I have this point here, x, f of x, down here, it's sort of mirror image point is negative x, the negative of f of x. So if I, this is 10 comma f, this will be negative 10, and then the negative of the f. That's a feature of odd functions. So an odd function is one where if I replace x with negative x, it changes the sign of the y value. I'll do a really simple one here. F of x is 4x cubed minus 6x. Okay, these are both odd functions because they're both of odd degree. So f of negative x is 4 times the cube of negative x minus 6 times negative x. That's going to be negative 4x cubed. That's going to be plus 6x, which is negative of 4x cubed minus 6x. So that's negative x, as it was supposed to be. So with that said, we're going to employ Euler's formula and then use the fact that sines and cosines are either odd or even. We know that. Sine is an odd function, cosine is an even function. So there's a lot of little tidbits of algebra that we need to remember sometimes to make the calculus work for us. Now, I'm going to substitute this into this equation. When I replace theta with negative ix, I'm going to get e to the I times negative ix. Well, I times negative I, we said a moment ago, is positive 1. So this is just e to the x. Oh, it's just e to the x. But on the other side, what am I going to get? I'm going to get the cosine of negative ix plus I times the sine of negative ix. Now, if x is a real number, then we know that I times x is imaginary. So anytime you have an imaginary angle, you're getting an e to the x. Oh my goodness. E to the x means you used imaginary angles, but e to the x is as real as it gets. You're right. If I use imaginary angles, I'll get e to the x back again. That is crazy, but it's true. Now, cosine is even. So the cosine of negative ix is the cosine of ix. The sine function is odd, so the sine of negative ix I know is the negative of the sine of ix. Therefore, this is equal to the hyperbolic cosine of x plus, remember, because the hyperbolic sine is negative I, so plus, whoa. The hyperbolic sines and cosines are sines and cosines of imaginary angles with weird stuff going on. Turns out here's a really important identity. This is true for the rest of your life. E to the x is equal to the sum of those. Whoa, right up here. Cool. Now let me do the same thing, but now I'm going to do it for positive ix. Positive ix, then that would make this e to the negative x. But if I go positive ix and I go positive ix, then what does that do? Well, I don't even need this line anymore. If I replace theta with positive ix, I'm going to get e to the negative x. E to the negative x is simply the hyperbolic cosine minus the hyperbolic sine. Oops. Okay, is that useful to me? Yeah, that's very useful. I don't need this line anymore. And here's a cool thing. You cannot calculate the sine and cosine of an imaginary angle. You can't calculate that directly. But e to the x, we should agree, is negative x. E to the x and e to the negative x are very, very easy to work with. There's nothing tricky about those. You suppose I could manipulate this and maybe write either the hyperbolic sine or the hyperbolic cosine in terms of e to the x? Anybody see a really obvious thing there? Because it's sitting right there in front of us. What would happen if I added those two equations together? If I add these two equations together, what do I get? I'd get e to the x plus e to the negative x is equal to, those would cancel, 2 times the hyperbolic cosine. That means simply that the hyperbolic cosine of x is 1/2 e to the x plus e to the negative x. And that's what your calculator did when it calculated the hyperbolic cosine of 4 a few minutes ago. It actually calculated that. Oh, so there's an alternate programming going on here. You see, if I want to calculate a hyperbolic function, I can't use the imaginary parts. I'm going to use Euler's formula to use the exponential parts. Now, what if I take the first equation and I subtract the second equation? Then the hyperbolic cosines will cancel and I'll get 2 hyperbolic sines. Ah, so the hyperbolic sine of x is 1/2 of e to the x minus e to the negative x. Cool. Now, the rest of the hyperbolics can also be assigned exponential versions. Now, unfortunately, okay, the way of the world is everything I'm showing you used to be taught in calculus courses a generation or two ago. Everything that I've shown you today, there's none of this in any calculus book written in the last 30 years. Unfortunately, all the stuff I'm showing you. You're not going to find it anywhere else. It's been removed from all the curriculum. It has been dumbed down significantly. It's been dumbed down to the point where most all calculus books now define the hyperbolics this way. Now, if you think about the logic, if a hyperbolic cosine is just a combination of e's, why are we calling it a cosine? Why are we calling it trig-ish at all? I can take these and add them together, and that's just a simple thing. Why would I call it some special? Well, it's because hyperbolic sines and cosines were sines and cosines of imaginary angles, and then I manipulate, use Euler's formula. I create these identities. These aren't the definitions. These are results of the previous stuff. But unfortunately, most textbooks use this. They don't use the imaginary parts. Is that a big deal? Yeah, when you get to differential equations and beyond, you're never going to use this. You're only going to use the imaginary parts, and you have to actually know what they mean. So I'm sitting there teaching a group of people in Math 255 who've never seen complex numbers applied. They're going to be a little behind because the textbooks are all written as if you know everything I've shown you, even though it's all been removed, which is kind of a problem. So I've got notes in great detail on the hyperbolics that are posted. They're a little hard to read if you hadn't seen what we're doing today. Now, when you're doing the derivatives, no, you don't need to change it to this. You just need to do what we did. There's one exception though. There's one exception. If we did the following, I want to differentiate, I want to keep it simple. I want to differentiate the hyperbolic sine of, x cubed. Keep it simple. Your answer, hyperbolic cosine of x cubed times 3x squared. That's it. You don't need to do anything else. You don't need to change this to anything else. Just leave it alone. Leave it alone. There is one exception, and this is the only exception. You never have to change these to this in order to use hyperbolics. You really don't. Unless your argument is a natural log. If your argument is a natural log, that means this guy right here, then you do want to change it. And I'll show you why. If I said I've got this hyperbolic sine of the natural log of x, yeah, the derivative is going to be hyperbolic cosine of the natural log times 1 over x. Great. Go back to here for a moment. Wouldn't this be 1/2 e to the natural log minus e to the negative natural log? Oh, and e to the natural log, they undo each other. So this is just 1/2 x. This negative moves up like an exponent. So that's x to the negative first, or hyperbolic sine of the natural log of x is equal to this quantity here. And I'd much rather take the derivative of that guy if I'm differentiating. The only time, and this is it, is if your argument is a natural log, then you would change your hyperbolic to the exponential version, because then you get a really nice simple function here. The rest of the time, no, just leave it alone. Totally okay. Now we're almost done. There's one more really, really cool thing about hyperbolics. The Pythagorean theorem. Now, a couple summers ago, I have it somewhere here. I was reading a book. It's called Why E equals MC squared. It was written by 2 Cambridge physicists. And it's really funny because when you start the book, it says you don't have to have a background in mathematics to understand the book. The book involves 4-dimensional geometry and non-Euclidean geometry. It's kind of funny. I barely understood the mathematics of the book. It is, yeah, it's a little bit hard for the average reader, but it deals with the complex Pythagorean theorem. And basically in the book, I learned things like, for example, if I run really, really, really fast, I will age slower than you guys. Now, it's not a lot slower, but they show there's simple examples. When that clock is moving on the train, you can actually prove time slowing down, and it just really cool, crazy stuff about, relativity and that kind of thing. But they were talking about the Pythagorean theorem in the complex realm, which I'm going to show you right now. It's a very cool thing. We know cos squared theta plus sine squared theta equals 1. We proved that on the first day of class when we reviewed our geometry. Now, we're assuming in this case that theta is real. Well, it turns out theta doesn't have to be real. Even for a complex theta, this statement is true. So the question is, how does this apply to the hyperbolics? If I said the cos squared of ix plus the sine squared of ix, is that still equal to 1? Well, it sure seems reasonable. Now, the hyperbolic cosine of x we know is the cosine of ix. Okay, so this is simply the square of the hyperbolic cosine. And by the way, I put the square right here. But this is not the square of the hyperbolic sine. Because the hyperbolic sine is negative I times the sine of ix, if I multiply both sides here by I, multiply both sides by I, we know that negative I times I is positive 1. So my right side is now the sine of ix. But my left side is now I times the hyperbolic sine. Oh, so sine squared ix would be I squared but that's negative 1. and the hyperbolic Pythagorean theorem, which is very cool. It's not the sum of the squares. This is true, but because of the I, it puts a negative. Whoa, that makes it really cool. Okay. Part of the reason they're called hyperbolics is because they do act like hyperbolas. There are certain properties of hyperbolas that these demonstrate when put together. So the hyperbolic Pythagorean theorem looks like this. So if you ever have, for example, 1 plus the hyperbolic sine squared or hyperbolic cosine squared minus 1, you can actually manipulate that and do stuff. It's, like I said, it's pretty cool stuff. All right, so your brains are probably hurting. They've probably swollen to an unusual size at this point. Whoop, here we go. The only two questions high schoolers would ever ask is, why do I need to know this? And of course, the follow-up, when am I ever going to use this? And I always used to say, if I can't answer both of those questions to your satisfaction, then you don't need to know it and you're never going to use it. If you're an engineer, turns out this is huge. Okay. Catenary. I think I spelled it correctly. A catenary is a hanging cable. The graph of the hyperbolic cosine, by the way, kind of looks almost like a parabola in a sense. It's kind of like this. We know, not just from experience, but also from experimentation and everything else, that all hanging cables have a particular quality. So let's say you wanted, you're at the top of a big building and you want to go across to another big building and you want to, have a rope going across. I want to tighten that rope to where it's absolutely perfectly straight horizontally. That's actually impossible. That would defy the laws of physics. You could never get that thing perfectly horizontal. Down to this, if I took a steel beam 10 foot thick and I went across, turns out the same thing. You can't have that thing before. There's going to be a dip. Even if it's down to the molecular level, it's called gravity. There's always going to be a dip. I want to take the strongest dental floss in the world and I'm going to tighten it. It's a simple law of physics that in the tightening process to make it perfectly straight, whatever you have would always snap, period. It's not possible to have perfectly straight. Everything is going to have some dip. It's the measure of the dip that's important. The graph of the hyperbolic cosine is the catenary. That is the thing that describes whatever a hanging cable is going to look like. I want to put a bridge. I want to put a beam. So how do you account for the dip? Well, there's a few things. Okay. I mean, the Romans figured this out with the aqueducts. You see, if you've ever been to Las Vegas, okay, I've been to Vegas several times, not recently, not to gamble, to actually compete in international karate tournaments. And they usually like to have the tournament, really nicely, MGM Grand, places like this, and they'll use the whole downstairs. Now, normally if you go, the downstairs, there'll be walls and partitions all over the place because there might be conventions and conferences, but they'll remove the walls. So you basically have, oh my gosh, almost the size of a football field of open space. So what's the big deal? And then 20 stories above you. So a simple question is, what's keeping the 20 stories above you from coming down and crashing down, since there's not even one support beam anywhere in this gigantical region? It's because they understand the mathematics of a catenary. You see, there are beams in the ceiling, but wouldn't they come crashing in the middle? Well, like the aqueducts, what do? They have them curve the other way so that the settling makes them straighter. It's actually pretty brilliant. The Romans figured this out. A lot of structures they figured out. That's what you've heard the term an arch. That's what an arch is. An arch gives you the support. So the weight of whatever it is keeps it together, but keeps it also from collapsing, because it's never going to be horizontal, because then you get the dip. So the study of hyperbolic cosines is part of what engineering, particularly, I believe it's structural engineering and mechanical engineers that use this. I hear all the time. It's something more complicated than just simply building a bridge, but understanding the mathematics of what's going to happen when you have something over a long extension. You got to be careful. You don't want it to be caving in the middle. So this is one of the reasons. So if you say, why do we need to know these? If you're an engineer, it turns out you actually really need to know this, but not for a while. You're not going to use these yet.